Hey, what does this symbol actually mean? And why is it really useful in our daily lives? In the previous video, we've talked about derivatives, function, limits, and the fundamental theorem of calculus. Now, let's talk about integrals. So, in the previous video, you saw that we can graph a function like this. This is the input, and this is the output, also written as f of x. Now, let's say a graph looks like this. I don't know what it is, but let's call it f of x. An integral basically means the total area under this curve. How much? We know that a function can go up to infinity unless it converges to a single value. So how do you even compute the integrals? This will be infinity or undefined in most of the cases like e to the x, 2x, x cubed, x squared, and lots of functions. So we don't really take the whole derivative, whole area, we represent it as a function, a big F of x, or let's define it as a of x. A means area, and this x really means this, and we have a boundary of this function. Let's say this is the 2 point in this function, its value, and this is the 4 point. So what it really means from 2 to 4 is we're trying to find the area under these two boundaries. Under this boundary. This is what integral means, and we represent it or try to represent it as a function so that we can find area between any intervals of x. So now let's talk about how do you compute them. In the previous video, I've also introduced a new topic, which is infinitesimal change in a function written as d of f of x, and infinitesimal change in x or dx. And this dx is the most useful thing here. So let's do this. Let's say this change in x is amount of dx. So if this is dx, this point would be f of x and f of x plus dx. As x dx is the infinitesimal change in the function or the x-axis or the input, this little area seems to have an area just like that rectangles. And this f of x plus dx and f of x doesn't really have any difference. They're both kind of same but a little bit off. So how can we define this area? As we know, this little width here is f of x. This little length here is f of x, and this little width or the infinitesimal change in the x is given by dx. This is just comes from the area of a rectangle, length times width. This is the length, this is the width, or whatever you say based on the orientation. But we're not interested in this little thing. This is very, very tiny, tinier than a single strand of hair. So what we'll be doing here is sum all these things. we're gonna take another thing here, another, and add up these all areas to get this. This curly S thing just means S, and S represents sum. What we're basically doing is summing up all those little areas, and this little area is just a function, and we want this function to define from a particular interval, like here in 2 to 4. Now it's the basic concept of integrations. Now here comes another fascinating part. Just like we know that sum is the opposite of subtraction, multiplication is the opposite of division, and integrals are opposite of derivatives. This is what we're going to be proving now. Now let's get back to our previous function or the previous graph. Draw it like this. And like this. Let's say this function is somewhat like this, I guess, on. Now, what we'll be again doing is getting an infinitesimally small area with the width of dx and the length of f of x. And as we defined earlier, the area between this is just a of x, but a little amount of a of x, so we can write it as d of f a of x. A little bit off, or a little change in the area function. Now, here this point is f of x plus h, this point is f of x. They're quite same, so this area just stays as a rectangle, approximately. But as we make this dx little and little, this area tends to be a rectangle, and that is why here's a d in front of the x. So we can say that the length of this rectangle is f of x and the width is dx. So the total area is f of x dx, and the little change in area, or as you can say, a of x plus h minus a of x. This is it. These two are the same. That a little bit change in the area function. Now what we'll be doing is not h but dx, also dx. H is a bit confusing. Here dx is much more easier to understand. Now divide both sides by dx. Why are we doing this? I don't know. F of x equals a of x plus dx minus a of x divided by dx. Hey, this is just a derivative of this area function. And if we take the derivative of the integral of the area function, we get back the previous function. This is what we call the swap of derivatives and integrals. This is it. Now we can prove all the formulas in integrals and derivatives with this little theorem. Now, let's move on to the first thing. Let's formalize it. Integral of f of x dx. Take the derivative of with respect to x, just give you df of f of x. Now, in our previous video, we saw that the derivative of x to the n is with respect to dx is just n times x to the power of n minus 1. How can this help us? Wait, now we'll be integrating x to the n. It's not a derivative anymore, it's an integral. Let's start with x squared. We like to use special cases so that it's easier for us to understand. The derivative of x squared is just 2 times x. 2 minus 1, which is just 1. We don't write 1 in the exponent. So, as we know that integrals and derivatives are the exact opposite, we're going to find which function has the derivative of x squared. If we find the function there, that will be our integral. Let's get back to the previous thing. Dx cubed with respect to dx has the derivative of 3x squared. Look, here's an x squared term. Here's also another x squared term. But here's a 3. But I don't see any 3 here. What can we do now? Wait, let's get to this. So we're going to be writing x squared in terms of this. X cubed dx times dx. Now, as you know, this little thing will just give us 3x squared. And another thing, as we know, that integrals and derivatives are interchangeable. So we just want x squared here. What if this function here has the integral of x cubed, but we're not interested in 3 here. What can we do? Wait. Just divide both sides by 1/3. 1/3. Yes, 1/3 here. 1/3 x cubed. This is it. Want to prove? Let's get x cubed. If we find the derivative of this x cubed, we get 3x squared. But notice here's an additional 1/3. 1/3. This 3 cancels out. We're left with just x squared. And this is the x squared. Now we're somewhere a very exciting place. Let's generalize this equation or this formula. Find the integral of x to the 4th dx. It's your homework to calculate it manually, but I'll just give you the answer. It's 1/5 x to the 5th. What's the integral of x to the 5th dx? It's just 1/6 x to the 6th. Did you notice the pattern here? If you didn't do, no problem. This is it. X to the n dx is just n plus 1 in the denominator and x to the n plus 1. Here notice, we did the exact opposite thing. Here we added 1 and here we subtracted 1. Here we multiplied by n, but here we divided by n plus 1. This is known as the power rule. Power rule of integrals. The previous thing here is called the power rule of derivatives. This is the power rule of integrals. Is it clear now? Let me know in the comment section if you want video on chain rules, integration by parts, and all the other things. That's all for today.